Okay, so,
I don't take art classes, I enjoy high school.
so today we're gonna finish up the last of this whole idea on, spontaneity and Gibbs free energy and all this thermodynamics stuff. So, we'll review tomorrow, test on Friday. So, when you look at delta G, so there's four ways that you can calculate delta G. One is the sums, that's the first one that's listed, okay? And you just did that on the lab. We just talked extensively about this equation, delta H minus T delta S, okay? Y'all have done that one back when we did redox reactions. We had the standard reduction chart, okay? So the odd one that's kind of lurking out there is this random one, which is negative RT times the natural log of K, okay? Which kind of doesn't make any sense. But I'm going to show you where that comes from. No, I'm not going to expect you to derive this equation. I'm just showing you the origin of it. So, if you look at, and it's a similar type thing, if you remember back to the Nernst equation, E equals E naught minus 0.0592 over N times the log of Q. Okay, remember that, right?
No.
Okay, trust me.
The nerd
Okay.
equation.
The Nernst equation. And so at equilibrium, we set E equal to 0. And then we were able to go through, and then we substituted K into there. And we ended up with equations for K. So this is where this thing goes full cycle. If K, the equilibrium constant, is a really small number, does that drive it towards the reaction being spontaneous, or driving it away from being spontaneous? If you have a really, really small K value, is that going to be spontaneous or not spontaneous?
No.
Not. Look at Ka values, okay, for weak acids, really small numbers. Look at KSP values for solubility, really small numbers. So if K values are small, the reaction doesn't happen. If K values are big, the reactions are favored in the forward direction. If K equals 1, you're at equilibrium, okay? So what I'm going to do is I'm going to take this equation. I want to do the same process. So at equilibrium, delta G is going to equal 0. So I got delta G naught plus RT times the natural log. Now, instead of Q, because I'm going to be talking about equilibrium, I'm going to have the K value, okay? So all I'm doing is just showing you where this comes from. So now, if I solve for, move that delta G naught over here, I subtract that over, I got delta G naught equals RT times the natural log of K. So then, you always talk about delta G by itself. So all I'm going to do is shift that negative sign over here to the natural log of K. So, here's the bigger idea. If K is a big value, this is where hopefully all this kind of comes together into one big idea. If K is a really, really big value, 1,000, whatever that is, if you take the natural log of a big number, is the natural log of a big number a positive or negative value? Positive or negative?
Positive.
Positive. You take the natural log of 1,000. If you don't believe me, take the natural log of 1,000. Okay? What's the natural log of 1,000?
6.9077552.
Big number, right? It's about 7.
Yeah.
Okay, it's about 7. So this is going to be a positive number if K equals 1,000. So that's a big number. It's a positive value. Because we're in Kelvin, what do you know about the temperature? Has to be a positive value, right? Oh, great. I got a positive value for the temperature. R is your gas law constant. Cool. That's joules per mole Kelvin. So I've got 3 positive values that I multiply together. Unless the laws of mathematics have changed, I still get a positive value. But then I get that negative sign out in front. Ooh, now what becomes the sign of delta G? Negative. Guess what? The reaction is spontaneous. Cool. Now, if K is a really small number, let's say K is, I don't know, 1.0 times 10 to the negative 4th. Ka value, it's a small number. Then when I take the natural log of a number less than 1, guess what? You get a negative number. Then you have a negative number times another negative number, you get a, and guess what? You get a positive delta G. Guess what? The reaction is not spontaneous. Okay? That's where it all comes together. Now I want to do a little bit of voodoo. Not much, but just a little bit. I want to get K by itself. So Sydney, I want to get K by itself. So what can I do?
Divide delta G by RT.
Okay, I'm going to move that negative sign up there. So there's my RT. Then what? So that's all gone. How do I undo natural log?
Take e to the power of whatever.
Beautiful. Okay. Okay. Now, this is where you have to pay attention to the units. Because if you get the delta G naught, guess what units that's going to be in? Typically coming out of that data table, that's going to be in kilojoules per mole. R is 8.314 joules per mole Kelvin, times your temperature in Kelvin. You cannot divide kilojoules by joules. It doesn't work. You need to make a decision. Multiply that joules by 1,000, do something, somehow involve 1,000. Either change that to joules, change that to kilojoules. I care not. It doesn't make any difference. But you cannot leave these in kilojoules and joules. Something has to be converted. Now, here's the bigger idea. If, and what you're ending up here is finding the value of K. Okay, this is what we're after, it's the value of K. And again, look at this mathematically. If
Just stop looking ahead of myself.
if delta G is a negative value, okay? If delta G is a negative value, then you're going to have a negative of a negative, which is going to make it positive. And then you're going to take e to a positive number, and mathematically, what are you going to get for the value of K? Big number or small number? Big number. Guess what? You're going to get a big number for K. It means the reaction is going to be spontaneous in the forward direction. If delta G is a positive number, then you're going to have a negative, right? That's why that negative sign is important. Then you can sit there and go, oh yeah, right, cool. Then I'm going to be taking e to a negative number. Guess what? Your K value then is going to be really, really small. Okay, so that's how it all fits together. Now, typically how this plays out, just with reactions with gases. So, you got delta G equals delta G naught plus RT times the natural log of Q. And And okay. So, let me explain the significance of this equation. It's actually known as the Haber process. The guy that developed it is kind of an anomaly in terms of how this guy Haber was perceived. So he actually won the Nobel Prize for this process. It's called the Haber process, where you take nitrogen and hydrogen and you produce ammonia out of it. And you wouldn't think, okay, hey, what's the big deal? The reason that he won the Nobel Prize for this, and this was in the 1920s, or 1910s, early 1900s, let's just settle on that, is that out of this equation you produce ammonia. So, and he was the one that figured out how to do this. It's a catalyzed reaction, and it's a weird element called osmium. And because why this is so important is that ammonia gets turned into ammonium nitrate, which is a fertilizer, okay? In one form, it's a fertilizer. And so this process, they figure, has literally saved millions of lives. Because what happens is that when you grow food in the soil, plants have to take up nitrates. There's biology, okay? And if you just keep growing the same crops in the same soil again and again and again, all the nitrates get depleted and the yield on the crop diminishes greatly, and the ground just basically becomes worthless. So, and farmers all over the world add ammonium nitrate to their soil. And what that does is that it replenishes the nitrates. But up to that point, nobody knew how to take nitrogen, very abundant element in our atmosphere, combine it with hydrogen to make ammonia. So Haber was the one that came up with this process. So in that regard, he was viewed as a hero because of the fact that, hey, here's a cheap way to make fertilizer that farmers can use to grow food. So in that regard, great guy. The reason he was also viewed as a villain at the same time is that ammonium nitrate is used as an explosive. And they used it in World War I, World War II, to kill people. So the same.
He didn't kill the people with the ammonium nitrate. Can't blame him for other people use it.
Oh, I know, but I'm just telling you. So they were literally, some of his fellow scientists would not attend when he won the Nobel Prize. Yeah, they would not attend the Nobel Prize ceremony because of how this was being used to create death.
Are you sure?
And so this process, which is vitally important, allows us to grow food, but it also used as an explosive. So it's this dichotomy that exists within science. It's like, here's the same equation. Are you going to use it for good or are you going to use it for evil? Okay, so here's your basic reaction. It's already balanced. You don't have to worry anything about it. And I've given you the delta G value. If you were not given the delta G naught value, you would have to go through and look up the thermodynamic properties and get delta G. It's a negative value. Is this spontaneous?
Yes.
Yes. Now, you know it's spontaneous. Now let's just step back for just a second. On the reactant side, you have 4 moles of gaseous reactant. On the product side, you have 2 moles of gaseous product. So you're going from 4 to 2. So what do you think the sign of delta S is going to, just based upon the reaction, before you do any calculations, what do you think the sign of delta S is going to be?
Negative.
Negative, right? It's a negative value. So you got a negative delta S, just based upon that. So is your delta S term driving it towards spontaneity? No, it's driving it away from spontaneity. So you look at the reaction, and here's what you should be able to handle as a thought process. You'll go, cool, I got a negative delta S. But I know the reaction's spontaneous, because I know I have a negative delta G. So is it possible that delta H is a positive value?
No,
Why not?
because you can't have a spontaneous, just can't make it spontaneous. You can't be spontaneous if delta H is positive and delta
Yeah,
S is
because that's never going to happen, because you have both things working against you.
Yeah.
So when you see that negative delta S, right away, what do you know that the sign of delta H has to be?
Negative.
So now I know I have to have a negative delta H with a negative delta S, okay? Just a simple idea. So is it an endothermic or exothermic reaction? It's exothermic because you know you're going to have a negative delta H. So the enthalpy term is driving it towards spontaneity. The entropy term is driving it away from spontaneity. Okay. So I'm going to tell you this is what you're going to do wrong. And you lie and you say you won't do this, okay? Kevin Watkins, you pay attention, because this is what you say you won't, but you lie.
No, I'm gonna forget to swear.
Okay.
Gonna forget to
You know
swear.
exactly, no,
Yep.
there's two things where this could turn into a train wreck.
Gonna forget.
Two things,
So it is going to. I'm gonna do them both.
okay? So, and then you've got RT, which is 8.314 joules per mole Kelvin. The temperature is, what's the temperature at? 389. No, yeah, that room temperature. 25 plus, what's 25 plus 273? 298. Now I'm running out of room. So here's what you gotta do. It's products over reactants.
Yeah.
So you've got your NH3, but there's a 2 in front of it. So Kevin, what are you gonna do?
You have to swear it.
You gotta square it. I ran out of room. I'm gonna put this on the end. So my NH3 is gonna be 0.5, but that's gonna get squared. And then you've got your M2, which is 1, not a big deal there. And then your H2, which is 3. But that's going to get Q. Okay? Now, before you do any calculations, couple of things. This is in kilojoules per mole. This is in joules per mole Kelvin. Can you add them together the way that is? No. And you all sit there and you go, oh, Mr. Burkamp, you're trying to be sneaky. We're not going to fall for your tricks, okay? We're not going to do this. We see your evil ways. And you all act cocky right now, okay? But come Friday, you all will forget that we ever had this discussion, okay?
What discussion? I'm dead.
Got it. So, I don't care what you do. Either change this into kilojoules, change that into joules, divide by 1,000, multiply by 1,000, I don't care. Pick one, okay? Now, but let's just look at this. You got 0.5 squared basically divided by 9. So is your Q value going to be bigger or smaller than 1? Smaller. So you're going to be taking the natural log of a value less than 1. So what's going to happen mathematically to this whole term? It's going to be positive or negative value. Gap, Sean, you just nod your head yes. That was an or question, not a yes-no question. Is it going to be positive or negative? Gap, Sean's doing this.
You did say
I said negative. I said negative. I whispered negative to myself.
So this is negative?
Yeah.
I was negative.
This is the international sign for negative natural
Yeah.
law. Okay, did not know that. Must have been on a TikTok video. So,
Can you imagine that?
So when you do this, if you go through all these numbers, you're gonna get a negative number. So is it spontaneous? Yes, because you're gonna get a negative value. Because it's actually gonna make it more negative. So sometimes what you ask is that, and sometimes you'll see this, if you look at delta, if you go back and delta G was delta H minus T delta S. So in this situation, you've got a negative delta H minus T, and then you've got a negative delta S, okay? So sometimes it will ask, and it's kind of weird how it's phrased, is that it'll say, is delta G gonna be more or less negative than delta H? So in this situation, because of the fact that you're in effect adding that T delta S term, then you would say that the delta G is going to be like less negative than the negative delta H term because that gets added. If that had been a positive delta S, then you would say the delta G term is less negative than that. Okay.
All done? Yay!
All done.
All done?
Yeah, we'll call it.
That never actually works.
I am so
Part of this, my voice.
All done. All
I
done.
have another week. Do you like my notes? Okay.
Okay. I've got 2 sheets of paper to hand out to